Welcome back to Quantumx. In today's video, we're kicking off a real-world project, building a shipping container home on 10 acres of land in Joshua Tree, California. The land belongs to Ben. It's a square parcel in a harsh desert environment, with a small hill right at the center, a factor that directly affects layout, foundations, container placement, and overall construction cost. If you're interested in hands-on construction, container homes, DIY, or off-grid living, this video gives you the big picture before any work begins, how land choice, structural thinking, and early decisions can make or break the entire build. Watch until the end of the video to witness firsthand the spectacular transformation of seemingly bland containers into incredibly warm and inviting living spaces. The project begins with the most fundamental step, site leveling. At Joshua Tree, the surface soil is uneven and heavily mixed with rock, forcing Ben and his construction crew to rely on heavy machinery from the outset. For the container home, Ben's team selected a monolithic concrete slab foundation. This approach suits the dry desert climate and effectively distributes the concentrated loads imposed by steel shipping containers. Excavation through rocky ground slows progress and demands precise control of slab elevation. Even minor inaccuracies at this stage can compromise every structure built above it. The foundation may not be visible once the build moves forward, but for Ben and his team, it defines whether the house will stand solid for decades to come. Wood is used to define the slab edges, while steel stakes are driven deep into the ground to prevent movement during the concrete pour. With the formwork secured, Ben and his crew move into one of the most critical structural phases, installing rebar according to the structural engineer's drawings. Steel bars are tied together to form a large reinforcing cage, which serves as the primary load-bearing framework of the monolithic slab. In a container home, the rebar must handle more than vertical loads. It also resists torsion and concentrated forces transferred from container corner castings. That's why bar spacing, elevation, and orientation are tightly controlled. A vapor barrier is laid across the entire excavation, preventing ground moisture from migrating up into the concrete slab over time. A layer of clean sand is then spread on top of the membrane. This protects the vapor barrier from damage and creates a level surface for the next steps. Concrete dobies are placed beneath the steel to keep the rebar lifted off the ground. This ensures proper concrete cover, reduces corrosion risk, and significantly extends the life of the foundation. At this stage, steel placement matters more than the concrete itself. During final preparation before the concrete pour, Ben and his crew make a key adjustment to the drainage system design. Instead of embedding the entire plumbing layout within the slab, they choose to leave only a single main drain penetration through the foundation. The reasoning is practical. In a container home, even a few centimeters of misalignment can turn plumbing installation into a costly problem, often requiring concrete cutting later on. By limiting slab penetrations, Ben reduces technical risk at an early stage. The remaining drainage system will be built within the container floor, where alignment, modification, and future maintenance are far more manageable. This approach isn't the fastest, but it prioritizes precision, flexibility, and long-term reliability. The concrete pour takes place on the same day Ben officially secures his building permit. From this moment on, all construction work moves forward under full regulatory approval. The crew pours 3 separate concrete slabs, each designed to match the layout and load requirements of individual container sections. One slab, located in a restricted area, requires a concrete pump rather than a direct truck pour. In total, 6 concrete trucks are used, delivering approximately 45 cubic yards of concrete. With this volume, timing, slump control, and pour sequence become critical to prevent cold joints and structural inconsistencies. This is a fast-paced, high-risk day on site. Once the concrete is placed, every decision made up to this point becomes permanent.
After 3 days of concrete curing, the site enters one of the most critical moments of the project, Crane Day. Ben brings in the largest crane used throughout the entire build to position the shipping containers onto the slabs. Specialized fabric lifting straps are attached to the container corner castings, distributing loads evenly and preventing torsion during the lift. The movement sequence is carefully planned. First comes a custom 20-foot container with a full side opening, used as a temporary material storage unit. Next is a 20-foot container designated for the guest bedroom and bathroom, lifted while being slowly walked into position. Finally, 2 much heavier 40-foot containers are set. These require multiple lifts, rotations, and repositioning attempts. In real-world conditions, placement accuracy reaches approximately plus or minus 0.5 inches, a strong indicator of precise coordination between crane operator and ground crew.
Once the containers are precisely set on the foundation, Ben and his crew begin direct structural work on the floors. The original plywood flooring, approximately 28 millimeters thick, is completely removed. Beneath it lies the factory-built steel joist system, coated with a protective layer designed to resist moisture and corrosion. To route the drainage system, certain steel members must be cut. This is not a step that can be done casually. Each cut location is carefully evaluated to avoid disrupting load paths and weakening the container floor structure. In a container home, the floor isn't just a walking surface, it's an integral part of the structural system. Proper removal, cutting, and reinforcement at this stage will determine whether the building performs reliably or develops long-term structural issues.
ABS piping is used for wastewater, a lightweight, durable material well-suited for drainage in container-based construction. Where pipes pass through steel members, foam and patching compound are applied to create a protective buffer. This isolates the pipes from sharp steel edges, reduces vibration, and prevents long-term abrasion damage. For the domestic water supply, Ben chooses copper piping. Although more expensive, copper offers superior heat resistance, pressure stability, and long-term reliability, especially in a hot, dry climate like Joshua Tree.
Once the plumbing system is complete, Ben and his crew move on to insulating the container floor. 2 layers of rigid foam insulation, each 2 inches thick, are installed directly over the steel floor framing. Any remaining gaps are sealed with spray foam to limit heat transfer and block insect intrusion. In a desert environment like Joshua Tree, this setup doesn't provide perfect insulation, but it significantly reduces thermal transfer from the ground and surrounding air. With the insulation in place, the container's original plywood flooring is reinstalled in its original position. This approach maintains the original floor height, preserves the container's structural integrity, and improves interior comfort without overcomplicating the build. When cutting openings for windows and doors, Ben and his crew face a major structural challenge. A shipping container is designed as a rigid steel box. Once sections of the wall are removed, the overall stiffness of the structure is significantly reduced. For this reason, every opening must be reinforced with additional steel framing. These frames do more than define the window or door. They transfer loads and replace the structural steel that was removed during cutting. Frame fabrication is performed in parallel with the cutting process, ensuring the container does not twist or deform while work is underway. In container construction, cutting an opening isn't just about creating access. Without proper reinforcement, each door or window can become a long-term structural weak point.
Welding technique becomes equally critical. Long, continuous welds are avoided to prevent distortion of the corrugated steel panels. Instead, intermittent welds are applied, typically 2 to 3 inches long, spaced 6 to 8 inches apart. Container cutting is carried out by Ben and his crew with a slow, controlled approach. They use angle grinders instead of plasma cutters, reducing thermal shock and allowing precise tracking of pre-marked cut lines. Cuts are made in short sections, prioritizing accuracy over speed. Inside the container, temperatures can reach around 120 degrees Fahrenheit, making the work physically demanding and highly disciplined. For the large bifold door system, Ben and his crew take no chances on rigidity. They use 3 by 2 inch rectangular steel tubing, heavier than typical framing, to ensure long-term strength and stability. When fully opened, a bifold door creates a wide structural span, concentrating loads and torsional forces along the frame. If the frame lacks stiffness, sagging and binding become inevitable over time. The entire frame is welded on a perfectly flat surface, with temporary bracing installed to hold alignment throughout the welding process.
When cutting large steel sections, Ben and his crew must contend with an often overlooked factor: residual stress within the container shell. Steel that has been under load for years can suddenly release tension once a cut is opened, causing panels to spring, bind the cutting blade, or shift unpredictably. For this reason, every cut is made slowly and under full control. Large openings are divided into smaller segments with support in place to manage the panel as it separates. Beyond internal stress, freshly cut steel edges are razor sharp, and the panels themselves carry significant weight. A single misstep can lead to serious injury or unintended structural damage. At this stage, skill isn't just about making the cut. It's about anticipating how the steel will behave once its internal stresses are released.
To meet permitting requirements, Ben and his crew reinforced the interior structure of the containers. Standard 2x4 wood framing is installed, combined with plywood shear walls to provide lateral resistance and overall stability. Above large door openings, oversized headers are added to prevent sagging and to properly redistribute loads. This reinforcement becomes mandatory once the container's original load-bearing shell has been cut. By design, a container gains its strength from continuous corrugated steel panels. When those panels are removed, the thin exterior steel, roughly 1/8 of an inch thick, can no longer be relied on as a primary structural system. More importantly, exterior steel is vulnerable to corrosion if not consistently maintained. No building authority will approve a structure that depends on the homeowner regularly repainting steel to keep it from failing. The added wood structure doesn't replace the container. It ensures long-term safety, code compliance, and structural reliability. Once large sections of the container are cut open, the original steel shell can no longer meet structural and permitting requirements on its own. At this stage, the interior wood framing must be mechanically tied to the container's steel structure. This is done using galvanized steel brackets, secured with self-drilling screws directly into the container's primary steel beams. Each connection point is designed to transfer loads effectively, resist lateral movement, and maintain overall structural stability. In practice, this is one of the most labor-intensive phases of the build. Container steel is hard, uneven, and offers limited access to structural members, making precise alignment difficult. Despite the effort, this step is non-negotiable. Building codes cannot rely on exterior steel that may corrode over time or on the homeowner's commitment to maintenance. The added wood structure ensures predictable performance, code compliance, and long-term safety independent of the container's exterior condition.
To meet structural and permitting requirements, the interior shear walls must be anchored directly to the concrete foundation rather than relying on the container shell alone. The solution involves steel anchor rods extending up from the slab, passing through the container floor and fastening directly into the wood studs of the shear wall. This creates a continuous load path, allowing lateral forces, such as wind and seismic loads, to transfer straight into the foundation. From a construction standpoint, Ben's team found that post-installed anchors using drilled holes and epoxy are far more practical than pre-setting bolts during the concrete pour. Real-world builds rarely align perfectly with drawings, and epoxy anchors allow precise placement after the shear walls are framed, reducing alignment errors and avoiding costly permit corrections. All welds are first coated with a rust-inhibiting primer, a critical step to prevent oxidation along exposed cut steel. Next, silicone sealant is applied continuously around the frame, and the windows are fastened directly into the steel rather than into wood framing. This approach minimizes material transitions, improves airtightness, and reduces movement caused by thermal expansion. This method is especially well suited to dry desert climates like Joshua Tree, where rainfall is minimal, humidity is low, but daily temperature swings are significant. Proper corrosion protection and flexible sealing ensure the windows remain tight, durable, and reliable over the long term.
During construction, Ben and his team refined the window frame design, switching from boxed steel tubing to angle steel with a flange. The change delivered immediate practical benefits on site. Angle steel makes alignment far easier, especially against container walls that are rarely perfectly flat. The flange also provides a solid edge for clamping and temporary fastening, improving accuracy during installation. More importantly, this profile allows for two independent caulk lines, interior and exterior, enhancing weather sealing and accommodating thermal movement. From a finishing standpoint, angle steel produces a cleaner, sharper edge, giving the windows a more refined and intentional look, an important detail for long-term performance and aesthetics in a desert environment.
For the large openings, Ben and his crew further reinforced and refined the steel frames by welding thin steel plates, approximately 1/8 inch thick, onto the existing box steel structure. This added layer increases localized stiffness while creating a clean visual separation between the flat door frame and the corrugated container skin.
More importantly, the detail doubles as a form of passive solar shading. The projecting steel edge helps block direct sunlight during peak sun angles, reducing heat gain through the glass, an effective strategy in desert conditions. The frame is also built with a slight slope, allowing rainwater to drain naturally and preventing water from pooling along weld seams, which helps extend the lifespan of the steel assembly. On location, Ben's team sets the door frame onto a pre-installed 1-inch wood base, establishing the correct elevation and isolating the system from direct steel contact. The frame is then carefully leveled and aligned using shims. With bifold systems, even minor misalignment can affect the movement of every panel, so accuracy at this stage is critical. Only after the frame is fully secured are the individual door panels installed onto the track. From a usability standpoint, Ben accepts that bifold doors require more effort than sliding doors. The trade-off is intentional. When fully opened, the interior space is almost completely unobstructed, delivering a level of openness and spatial connection that few other systems can match. Once the doors are fully installed, attention shifts to sealing the gaps around the frames. For exterior gaps, Ben's team uses fire-rated expanding foam, since steel welding is still ongoing in these areas, and the material must resist heat and ignition. Next, angle steel and flat steel plates are welded in place to cover the foam and exposed wood framing, protecting the assembly while creating a clean, finished edge. All newly welded steel components are then coated with a rust-inhibiting primer, sealing off cut edges and weld seams from corrosion. Alongside the large bifold system, the remaining entry doors are installed as well. All of them are glazed patio-style swing doors, chosen to bring more natural light into the interior, an important consideration for container structures with largely solid steel walls. The installation follows the same technical principles: precise frame alignment, thorough weather sealing, and rust protective primer applied to all cut and welded steel surfaces. Each opening is treated as a potential weak point in the container envelope, making waterproofing and corrosion protection just as critical as appearance. Once completed, these patio doors strike a balance between daylighting performance, thermal control, and long-term durability in a harsh desert environment. First, silicone sealant is applied continuously inside the steel frame, forming the primary waterproof barrier between the steel and the window unit. The window is then fastened directly through its mounting flange into the steel frame, providing a solid, long-term connection. Only after the exterior is fully secured does the team add a 2x4 wood frame on the interior, reinforcing the opening and creating a clean surface for future interior finishes. Around openings, they use great stuff low-expansion foam, specifically chosen to avoid distorting door and window frames as the foam cures. The foam is applied continuously into remaining gaps, especially in corners and tight areas where rigid insulation cannot be installed. The primary goal here isn't just thermal insulation, but reducing air infiltration, a major factor in energy loss for container homes. Electrical boxes are installed, wiring is run through the interior framing, and this is the last opportunity to verify and adjust the placement of outlets and switches before the walls are closed. For insulation, Ben chose not to rely entirely on spray foam, instead opting for rigid foam insulation to allow for hands-on installation and tighter quality control. Multiple thicknesses, 2-inch, 1-inch, and 1/2-inch foam boards are combined to maximize insulation performance within the tight interior dimensions of a container. Before committing to the full build, the team completed a test wall section. This mock-up allowed them to refine layering techniques, address gaps, and evaluate real-world installation challenges. Initially, OSB was used as the interior sheathing, but it was later replaced with plywood due to its lower formaldehyde content, improving indoor air quality, an important consideration in a compact, airtight container home.
During insulation work, Ben and his crew ran into a common spray foam issue. In several large gaps, applying too much foam at once caused it to expand uncontrollably, spilling out and complicating later finishing work. From this, they identified a few clear lessons. First, apply foam slowly in thin passes rather than trying to fill the void in one shot. Second, lightly mist the surface with water, helping the foam expand more evenly and cure properly. Most importantly, for larger gaps, insert rigid foam first, then use expanding foam only to seal the remaining edges. These small adjustments make the process far more predictable and save significant time during cleanup and finishing.
For the floor insulation, Ben uses two different approaches depending on the container. In one unit, the floor is built with OSB bonded to foam panels using a specialized construction adhesive, creating a fast, solid, and continuous surface. In the second container, a more traditional system is used: 2x4 framing, infilled with foam insulation, then finished with plywood. This method offers greater flexibility for utilities and fine floor leveling. Labor strategy plays a key role here. Ben hires out the carpentry, plywood, and insulation work, where skilled labor is easier to source at reasonable cost. He personally handles steel and welding, knowing that experienced welders are hard to find cheaply, and weld quality directly impacts long-term structural safety. In the finishing phase, Ben focuses on small but critical steel details, including thin, flat steel window frames for the bedroom. These frames are slightly sloped by design, allowing rainwater to drain away and preventing moisture from pooling along steel edges, a common cause of long-term corrosion. All welding work is done using a Forney 3-in-1 welder, providing the flexibility to cut, weld, and fine-tune details directly on site. In container construction, durability is often determined by these details rather than large structural elements. Clean welds, proper drainage, and careful steel protection ensure the system performs reliably in a desert environment with extreme day-night temperature swings. Forklift pockets and other large openings at the container ends are covered with flat steel plates fully welded to restore the continuity of the steel envelope. Areas where plumbing lines pass through steel beams, previously cut to allow routing, are also patched and reinforced. The goal goes beyond appearance. It's about blocking water, air, and pests while eliminating potential starting points for corrosion. Per the structural engineer's requirements, all interior walls are sheathed with half-inch plywood to contribute to the building's lateral load resistance. In a container home, this layer helps restore structural capacity after large openings are cut, while offering a practical benefit: easy mounting for cabinets, shelving, and fixtures without hunting for studs or drilling into steel. At the same time, the sprinkler system, mandated by code, must be installed. All piping and sprinkler heads are set in place before the ceiling insulation is completed, since access becomes extremely limited once the ceiling is closed. Once all systems are installed and inspected, Ben moves on to drywall finishing. Rather than doing it himself, he brings in a professional crew to handle the entire process, hanging the drywall panels, taping and mudding the joints, and applying a full skim coat. The reasoning is straightforward. This phase demands skill, speed, and consistency, and experienced drywallers deliver results that are difficult to match with DIY methods. In just 2 days, the entire interior is transformed into a smooth, paint-ready surface. In a self-build project, knowing when to hire professionals can save time, reduce fatigue, and significantly improve the final outcome. Where does the waste go? If you're building a home out in nature with no access to a municipal sewer system, this isn't a side question. It's the foundation of the entire building system. And for this house, the answer... Ben's original plan was to install a traditional leach field, relying on natural soil absorption to handle wastewater. This system is common in rural areas, valued for its simplicity and minimal mechanical dependence. To confirm whether the site could support it, the crew carried out exploratory drilling, excavated test pits, and sent soil samples to a laboratory as part of the percolation testing process. The results were clear. The site failed the percolation test. The soil showed poor drainage capacity, and solid rock was encountered just beneath the surface, preventing proper infiltration. Under these conditions, a conventional leach field would be unreliable and unsafe. This outcome forced Ben to abandon the original plan and reconsider the entire wastewater strategy, choosing a system better suited to the harsh geological realities of the Joshua Tree landscape.
The final solution was a custom-designed septic system. All wastewater, from toilets, sinks, and showers, flows through a 3-inch drain line into a 1,500-gallon concrete septic tank located approximately 60 feet from the house. Inside the tank, waste naturally separates into 3 distinct layers. The scum layer, made up of grease, oils, and soap residue, floats at the top. The sludge layer, consisting of solids, settles at the bottom. Between them is the effluent, liquid wastewater containing bacteria along with nitrogen and phosphorus. Instead of relying on soil absorption, the effluent is pumped into 4 precast concrete planter boxes, where it is reused for irrigation and biological treatment. This approach reduces the load on the septic tank, prevents rapid filling, and creates a controlled, above-ground wastewater solution suited to the site's rocky conditions. The next phase involved installing 4 precast concrete planter boxes, which serve as the biological treatment stage for the septic effluent. The planters were aligned in a straight row on a leveled base, excavated to a depth of approximately 8 inches to ensure stability and proper drainage. Each planter was built with 2 dedicated penetrations. The first is the effluent inlet, allowing treated wastewater to float in from the septic tank. The second is an overflow outlet, acting as a fail-safe in case water levels rise beyond design limits. This configuration allows the system to operate in a controlled manner, preventing localized overload while distributing effluent evenly across the planters. The result is a passive, above-ground treatment solution that promotes gradual absorption and biological processing, a practical response to the site's shallow soil and underlying rock. The piping system was designed to be simple, yet highly controlled. A 2-inch ABS pipe serves as the overflow line, routing excess effluent back to the septic tank if the planter boxes reach capacity. Inside each planter, the effluent distribution pipe is positioned near the top, allowing wastewater to spread evenly rather than concentrating at a single discharge point. Below, a layered system of gravel and geotextile fabric provides mechanical filtration while preventing fine soil and plant roots from entering the piping. The system is completed with a submersible pump installed inside the septic tank, controlled by a float switch. When effluent levels rise, the pump activates automatically, pushing wastewater through a 1-inch polyethylene line to the planter boxes above. Each planter is equipped with an individual flow control valve, allowing precise regulation and preventing localized overload. The next step was filling the 4 planter boxes with growing media to complete the biological treatment system. Most of the volume was filled with low-cost soil, selected for adequate drainage and bulk fill rather than nutrient content. This approach significantly reduced material costs while still meeting functional requirements. On top, a dedicated layer of topsoil was added to establish a living environment for plants and microorganisms. This upper layer is critical. It supports aerobic bacteria and root systems that help break down nutrients and further treat the effluent. A base layer of 3/4-inch gravel surrounds the piping, promoting rapid drainage and protecting the pipes from compression or clogging. Next, perforated ABS piping was installed to distribute effluent evenly across the planter, rather than releasing it at a single point. This ensures gradual infiltration throughout the growing media, maximizing biological treatment efficiency. The top layer consists of finished soil, followed by the seeding of wildflowers. Beyond aesthetics, this vegetation plays a functional role. Plant roots and microorganisms work together to absorb excess nutrients and stabilize moisture levels. The result is a planter system that functions both as a visual landscape feature and as an integral component of the wastewater treatment process, closing the loop between infrastructure and environment. The next step was connecting the house to the electrical grid. Power lines were run underground from the utility pole through the meter and directly into the home's main electrical panel. Because the container home sits on a concrete foundation, the crew had to cut a trench directly into the slab so the conduit could run tight against the container structure. From a technical standpoint, the conduit route had to be almost perfectly straight, allowing only a single 90-degree bend. This minimizes wire pulling resistance and meets utility company requirements. The conduit was buried approximately 4 feet deep, protecting it from temperature extremes, erosion, and mechanical damage. Once positioned, fast-setting concrete, Quickcrete, was poured immediately to lock the conduit in place, ensuring stability before the electrical pole and final inspection.
After the water meter was installed, the plumbing system was brought online by running underground supply lines into the house, then splitting them into 2 separate entry points for the container structure. This layout shortens interior runs and allows easier isolation for maintenance. The entire home is served by an on-demand electric water heater, providing continuous hot water without the need for storage tanks. For materials, PVC piping was used underground, while copper pipes were installed near the surface and inside the house for durability and heat resistance. All copper soldering was handled by licensed professionals to minimize the risk of long-term leaks. A 20-foot container was designated as the laundry and mechanical room, housing the Ream water heater. Despite the distance from fixtures, the system delivers consistent performance, proving well-suited for a compact, container-based layout. The heating and cooling system, HVAC, is based on ductless mini-split heat pumps, a practical choice for container homes where space is limited and energy efficiency matters. Each system consists of 2 main components, an outdoor condenser and 1 or more indoor air handlers. In terms of layout, the living room and bedroom are served by 2 air handlers connected to a single condenser. The living room uses a ceiling-mounted air handler, providing even air distribution while maintaining a clean interior profile. The office and storage area rely on 2 wall-mounted air handlers paired with a separate condenser. Because the containers are arranged as independent units, some refrigerant and control lines had to be buried underground to connect the systems. This approach protects the lines, maintains a clean exterior, and ensures reliable HVAC performance across the entire structure. Once the doors and windows were installed, surface preparation for painting began. Gaps between the steel frames and the container shell were sealed using fire-blocking spray foam, specifically chosen to withstand heat and avoid damage during subsequent welding. Steel trim pieces were then welded in place to cover the foam and clean up the cut edges of the container, creating a continuous and durable transition. Before any coating was applied, all exposed steel surfaces were thoroughly prepped. This involved removing mill scale and surface rust using angle grinders and abrasive pads. To complete the process, the steel was wiped down with mineral spirits, eliminating fine dust and residual oils. This final cleaning step is critical, ensuring proper paint adhesion and long-term protection in the harsh desert environment. For the priming stage, the crew chose a rusty metal primer, which proved faster and more effective than standard metal primers. This type of primer is well suited for container steel, where traces of mill scale and oxidation risks remain even after surface prep. It can bond directly to properly cleaned metal, reducing cure time and minimizing the number of required coats. Once the primer had fully cured, all joints and seams were sealed using GE paintable silicone. This step is critical for locking out water and air before moving on to the final paint coats. The plumbing vent pipes were carefully sealed to prevent water intrusion. Foam was applied around the penetrations to close gaps and secure the pipes, followed by custom-shaped metal flashing to divert rainwater away. All seams were sealed with silicone, and a final coat of Henry stop-leak roofing spray created a continuous waterproof membrane, ensuring long-term protection against leaks. The exterior painting was handled by a professional crew to ensure consistent coverage and long-term durability. PPG Timeless Exterior Paint in Elegant Charcoal was chosen, finished in a flat matte texture to reduce glare and hide surface imperfections. Each coat took roughly 1 day to apply, yet the finish came out clean, even, and highly precise. Inside the house, PPG Crystal Clear White was used with a flat finish, creating a bright, modern interior that reflects natural light effectively. One standout detail is how the exterior gray shifts subtly depending on lighting conditions throughout the day, giving the home a refined, high-end architectural feel.
By design, the container only bears on the foundation at the corner blocks, leaving a continuous gap of roughly 1/4 inch along the perimeter. The process starts by applying spray foam to act as a backing layer and flexible buffer. Once cured, the excess foam is trimmed flush for a clean edge. The gap is then fully sealed using Quikrete precision grout, creating a solid, finished transition between the container and the foundation. This step not only improves the visual finish of the structure, but also serves a critical function, preventing insects and small animals from accessing the crawl space beneath the home.
Anchoring the container to the concrete foundation is a mandatory requirement for seismic resistance and to prevent movement that could damage electrical and plumbing systems. The process begins by drilling 72 holes through the steel, each measuring 1 inch in diameter. The chosen solution uses 3/4 inch thick steel angles, combined with steel plates, threaded rods, and high-strength concrete anchoring epoxy. The concrete foundation is drilled to 1¼ inches in diameter and approximately 1 foot deep. High-strength epoxy, rated for around 28,000 pounds of tensile load, is injected before inserting the threaded rods. Once the epoxy fully cures, the steel is welded in place, forming a rigid and permanent structural connection. Steel plates are then welded directly to the container's corner blocks by a certified welder.
The kitchen installation sequence follows a structured approach to ensure accuracy, durability, and clean finishes. Cabinets are installed after drywall is completed but before flooring, allowing them to sit directly on the structural base rather than the finished floor. This prevents height inconsistencies and makes future floor replacement easier. Behind the lower kitchen cabinets, moisture-resistant green board is used to protect areas exposed to water and humidity. During installation, cabinet doors are removed to prevent scratches, reduce weight, and allow precise alignment. Since real-world floors and walls are never perfectly level or straight, installers rely on shims to level and square the cabinets. This step is critical to ensure consistent cabinet lines, smooth door operation, and a properly fitted countertop once installation is complete.
Ben built the reinforcement panel for the waterfall edge himself to ensure structural strength and precise stone installation. The panel was assembled using laminated plywood with a total thickness of 1.5 inches, creating a rigid load-bearing surface capable of supporting the heavy stone slab without long-term deflection. In addition, poplar trim strips were added to create the required clearance for a built-in refrigerator, allowing proper ventilation and easier appliance alignment. The reinforced panel was installed in its final position before the stone contractor arrived. This allowed the stone team to take exact field measurements for the waterfall edge, minimizing fabrication errors, reducing the need for on-site adjustments, and ensuring clean, tight joints with a high-end architectural finish. The stone installation team began by using thin Lewin plywood to create precise on-site templates for the countertops, waterfall edge, and complex cutouts. This templating process is critical because walls and cabinets are rarely perfectly square, and accuracy directly affects the final fit and finish. A floating shelf was installed on the wall above the kitchen sink area to increase functional storage while adding a clean architectural accent to the kitchen. Before installation, the shelf location was carefully aligned with the sink and base cabinets to maintain visual balance and practical usability. The shelf was anchored directly into the structural framing behind the drywall, not just the gypsum board, ensuring it could safely support dishes, decor, and frequently used kitchen items. The vertical spacing between the shelf and the sink was intentionally planned to avoid interference during washing, while minimizing water splash exposure. This floating shelf solution keeps the kitchen feeling open, light, and uncluttered, reinforcing the modern, minimalist aesthetic of the overall interior design.
Once templated, the countertops were fabricated from silestone quartz in White Zeus Extreme, then transported back for installation. An undermount stainless steel sink was mounted beneath the quartz to create a seamless, easy-to-clean surface. The team carefully drilled openings for the faucet and garbage disposal switch, ensuring proper alignment and clean edges. The result is a high-end, precision-installed stone surface that elevates both the functionality and architectural quality of the kitchen. The Backsplash features an asymmetrical hex tile layout, serving as a key visual focal point in the kitchen. Instead of a traditional straight or uniform pattern, the tiles are intentionally offset to create rhythm, movement, and visual depth. This approach adds character and prevents the backsplash from feeling flat or repetitive. The pantry was built using a combination of Thomasville cabinetry and solid oak shelving, balancing storage efficiency with warm, natural materials. Because the pantry space is only 12 inches deep, upper-style cabinets were selected to maximize storage while maintaining clear circulation and a clean profile. A 2x4 framing system was carefully constructed and leveled to ensure all cabinet faces aligned perfectly before installation. Because the container is relatively narrow, with only about 7 feet of clear width remaining after insulation and wall framing, Ben chose a galley kitchen layout as the most efficient solution. One side of the kitchen is dedicated entirely to the cooking zone, with a continuous run of countertop, integrating the cooktop, sink, and prep area. The opposite side features a mix of base cabinets and open shelving, functioning as an extended pantry wall. Ben intentionally avoided making the entire kitchen solid white cabinetry, as that approach can feel visually heavy in a tight space. Instead, he balanced closed storage with open shelves, allowing the space to breathe while still meeting functional needs. This mix creates a kitchen that feels lighter, more modern, and visually dynamic, maximizing usability without sacrificing openness, a crucial design strategy when working within the strict dimensions of a shipping container home. The oak shelves received detailed finishing work, sanded to 220 grit, then sealed with simple finish, a plant-based oil that preserves the wood's natural color and grain without adding artificial shine. To complete the design, each shelf was trimmed with 1x2 oak molding, creating a subtle framed effect. This detail adds depth and craftsmanship, transforming a compact pantry into a refined, built-in architectural feature rather than a purely utilitarian space.
Next, let's find out how Ben built the bathroom for this container house. Don't forget to like, share, and subscribe to the channel to support us.
The bathroom is located between the kitchen and the bedroom, using a walk-through layout to eliminate wasted hallway space. This is a highly intentional design move, maximizing every square foot inside a container where space is inherently limited. All major mechanical systems are concentrated behind the bathroom wall. Drain and vent lines are run in black ABS piping, routed directly to the septic system and up through the roof to meet proper venting requirements. Water supply lines are installed using copper, chosen for durability and heat resistance. The smart shower system introduces an important technical detail. Its control valve requires a dedicated access panel behind the wall. This allows future maintenance without opening finished tile or walls, a small but critical decision that reflects real-world construction experience and long-term serviceability planning. The bathroom wall assembly was designed with a clear priority on long-term durability and moisture resistance, not just minimum code compliance. The innermost layer is plywood, providing structural strength and allowing heavy fixtures and accessories to be securely mounted without relying solely on drywall. Over the plywood, Ben installed moisture-resistant green board, specifically intended for wet areas to reduce water absorption over time. The entire surface was then coated with Rebar, a liquid-applied waterproofing membrane that creates a continuous barrier against moisture intrusion.
Tile installation began only after the waterproofing system was fully cured. Ben selected mini hex tiles mounted on mesh sheets, a choice that balances strong visual impact with improved installation accuracy. This format is especially effective in tight bathroom spaces with multiple cuts and penetrations, common in container builds.
For the bathroom floor, Ben avoided installing tile directly over the container's original wood subfloor. Instead, he added a cement board underlayment, creating a stable, moisture-resistant surface that significantly reduces the risk of tile cracking caused by material movement. This step is essential for long-term performance in wet environments. For grouting, the crew used Fusion Pro Grout in white, a pre-mixed product that eliminates on-site mixing and ensures consistent quality. Its key advantages are high stain resistance and a degree of built-in flexibility, allowing the grout joints to accommodate minor structural movement. The transition between tile and wood flooring was treated as a critical construction detail, affecting both durability and visual quality. Instead of using a standard transition strip, Ben's crew hand-cut the hex tile mesh, creating a more organic and natural edge that suits the walk-through bathroom layout. To achieve a perfectly flush floor height, plywood was used to raise the wood flooring to match the finished tile elevation. This step required precise thickness calculations to avoid uneven surfaces. Before cutting the final wood flooring, the team built a physical template using leftover tiles, placing it directly on site to capture the exact transition shape. This approach is more time-consuming, but it results in a clean, seamless junction that feels intentional and refined, a small detail that clearly separates careful craftsmanship from shortcut construction. The flooring was finished using engineered wood, a smart choice for container homes due to its dimensional stability under temperature and humidity changes. Instead of a floating or click-lock system, Ben opted for a full glue-down installation using construction adhesive, ensuring a solid bond and minimizing future movement or noise. During installation, heavy weights were placed on top of the boards to hold them firmly in place while the adhesive cured. This step is critical for achieving consistent contact and preventing edge lift. For tight corners and curved transition areas, the crew relied on a multi-tool, which allows precise cuts without damaging the finished surface. This method takes more time, but it delivers a cleaner, more durable result, well suited to the tight tolerances and detailed layouts typical of container-based construction.
In the final finishing stage, special attention was given to the transition between the tile and wood flooring. Rather than using a metal trim or standard sealant, Ben chose to grout the joint using Fusion Pro.
Once the flooring and tile work were complete, Ben moved on to installing the toilet and vanity, marking the final stage of the bathroom build. Because the plumbing rough-in had been carefully planned earlier, all supply and drain connections aligned cleanly without the need for structural adjustments.
Mounting the mirror and bathroom accessories proved to be more challenging than it appears. Drilling through finished tile requires precise layout and careful execution, as even a slight misalignment can crack tile or throw off the visual balance. Behind the tile sits a structural plywood layer, so both drill speed and pressure must be controlled to avoid damaging the wall assembly. During the door installation phase, Ben chose a pocket door between the kitchen and the bathroom. However, a pocket door was not used on the bedroom side. The reason is purely technical. That wall contains the smart shower control system, which requires clear access for maintenance. Instead of sealing it behind a permanent wall, Ben incorporated a hidden access door, allowing service without disturbing finished surfaces. The primary bedroom was designed around storage efficiency and spatial comfort. Ben raised the bed platform by approximately 30 centimeters, creating concealed storage underneath for luggage and bulky items. The platform frame is built from 2x6 lumber, anchored directly into walls reinforced with plywood and studs, ensuring long-term structural stability. The surface is finished with oak veneered plywood, stained antique white, and sealed with polyurethane for durability. The front edge is wrapped in solid oak trim, with all fasteners hidden using wood filler for a clean, furniture-grade finish. A canopy-style fabric treatment adds warmth and softness to the space. The ceiling is lowered to conceal the ductless HVAC air handler, keeping mechanical systems out of sight. With an interior area of roughly 140 square feet, Ben prioritized daylight by installing parallel glass doors, allowing abundant natural light and effective cross-ventilation.
The second bedroom was completed with a more practical and simplified approach compared to the primary suite. Minor floor imperfections were concealed using a 2x6 wood beam paired with white trim, which also doubles as a small ledge for phone charging and personal items. The overall layout follows the same design language as the main bedroom, but in a more restrained form suited to a secondary space. A low shelf beneath the window adds functional storage without consuming usable floor area. Electrical planning was carefully considered, with multiple outlets and grommeted cable pass-throughs to keep cords organized and out of sight. Ben also clarifies that ventilation holes beneath the bed platform are unnecessary when using a tufted mattress, as this mattress type already allows sufficient airflow through its construction.
From an empty desert lot in Joshua Tree, Ben and his crew methodically transformed raw steel containers into a fully functional, technically sound living space. This video isn't just about building, it's about design thinking, real-world problem solving, and the trade-offs required when constructing off-grid and off-the-beaten path. If you're interested in container homes, DIY construction, or unconventional building strategies, take a closer look at the details and draw your own lessons from the process. If you found value in this project, like the video, share it with others, and leave a comment with your thoughts or questions. And don't forget to subscribe to Quantumx for more in-depth, real-world construction breakdowns. Thank you for watching.